hours. I'll probably give a 2-hour midterm, but let's keep a 3-hour block. So if extra time is needed, I can give and so on. Okay, so you people can use the teams to discuss among yourselves and decide. Okay, yeah, and okay, so that's one small thing, and the yeah, okay. So any questions or anything so far? Okay, so I hope people are following. Yeah, so let me continue in that case. So what is there a question? Okay, so I didn't start recording. So let me see. Oh, I have started recording. Okay, somebody did. Okay, so far what have we done? We have constructed measures. Why in several ways, or maybe not several, but a couple of ways. So we can start with some basic sets and extend the measure to a sigma algebra. One way is by checking countable additivity on the algebra. So you construct a set functional from an algebra to positive real numbers, which is countably additive. Then you can extend it to a measure on the sigma algebra containing it. And another way is that if you have an outer measure which has this metric property, that is, it is additive when two sets are separated from each other, then again it extends to a sigma algebra on the Boyle sigma algebra of that metric space. Okay, so these are two theorems we saw. So after that I decided I will come to Lebesgue measure. Many things I can do also in generality, but let us be very specific and understand Lebesgue measure on Rn. Okay, so let's understand Lebesgue measure on Rn. First of all, I was constructing it, so more or less it is done. There is not much to do, but I just want to tell. Maybe we do a quick recap of this and then go on to studying properties of Lebesgue measure. So how is Lebesgue measure on Rd to be constructed? Idea is, okay, we start with Rd, that is our set, and we start with a collection of left open, right closed rectangles, which are I1 of this form, where each I1, I2, Id is a left open, right closed interval like this, rectangle like this. Okay, so the algebra generated, this is a pi system. The set of rectangles is a pi system because intersection of two such things is another object of the same kind. Therefore, that's a pi system. The algebra generated by that is actually the collection of all finite unions of rectangles, where these are left open, right closed rectangles. That is because the complement of any of these things can be written as a finite union of such things. That's the reason. Okay. So the sigma algebra generated by this collection is the same as the Boyle sigma algebra. There is no doubt about that. Now, what is it that we do? We start with the lengths defined on rectangles that will be defined in the obvious way as the length of the sides, product of the lengths of the sides. That's how we define the length, area or volume of a rectangle. And then on the algebra, how do we define? Every element in the algebra is a finite union of pairwise disjoint rectangles. So it's obvious I have to define the volume of that to be the sum of the volumes of the component rectangles. That's how I try to define. From here, so now there are two ways to go. One way, let us check. One way is we check that this thing is countably additive on the algebra, and therefore it extends to the sigma algebra, or it extends to a larger collection which contains the sigma algebra generated by these rectangles, namely the Boyle sigma algebra. Okay, so how do we check the countable additivity? Now, one point here is that well-definedness has to be checked. After that, finite additivity is easy. And I was coming to countable additivity and I ran out of time, so I skipped that. So I just want to go over how countable additivity is checked now. And for that, we will use the criterion that we used last time. So there was this criterion that, right. So here was a criterion to check countable additivity. Suppose we have an algebra and we have this thing on it which is already finitely additive. We have checked that. Then to go to countable additivity on the algebra, what we have to check is two things. If you have a set with infinite measure, that is mu of a is infinity, all you need is that you should have inside it algebra elements which have finite measure and whose measures increase to infinity. That is one. Second is if you have a set of finite measure, then given any epsilon, you can sandwich like this, one compact set contained in A, which contains, then the compact set should contain a set in the algebra B, such that the measure of B is very close to measure of A within epsilon of it, not too small. So these are the conditions we have to check, then we are done. Then it follows that countable additivity. We proved it last time. So it's much easier to check this than directly check countable additivity. So that's why I want to show how this is checked. Okay, so we'll check this. So let's check why this is countably additive.
Sir, can I ask one question?
Yes.
So, sir, this LD star contains Borel sigma algebra. That is not immediately clear, right? Because any open rectangle, I can, write it as a countable or finite union of LORC rectangle. But how about any arbitrary open set in the
No. LD, what did we prove about the extension theorem? Said that it extends to a sigma algebra that if mu is okay. Firstly, an outer measure gives a measure on the sigma algebra L, which is the collection of things that satisfy the characteristic cut condition. But then there was another statement that if it so happens that mu is to start with countably additive on the algebra, if A is an algebra and mu is countably additive, then that L mu star, that sigma algebra, contains the algebra itself. Therefore, it contains the sigma algebra. Since this is a sigma algebra that contains A, it contains the sigma algebra generated by the algebra. Now, in our case, we will check countable additivity. Therefore, it will contain the sigma algebra generated by rectangles, which is the Borel sigma algebra. Is that clear?
Okay. But sir, Borel set is basically sigma algebra generated by any open set in RD, right? And not just open rectangles.
No. Don't say by any open set. Let us be very clear. Borel sigma algebra is the sigma algebra generated by the collection of open sets in RD.
Okay, so that means that
let us stick to R. Let us take Borel sigma algebra on R. It is the sigma algebra generated by the collection of open sets. Now, is it true that if I take what is the sigma algebra generated by, let us say, closed intervals?
Closed interval,
It is also the Borel sigma algebra for reasons which I discussed earlier, but if it is not clear, let me say here. Yes.
I think the point that they were trying to make is slightly different in the sense that in a one-dimensional space, the only open sets you can have are intervals. But on a two-dimensional space, you can have all kinds of weird shapes that are not necessarily rectangles that are still open sets. I think it has to do with the set of open rectangles being a basis for the topology of R2, but I am not entirely sure.
Okay. Let's do it in RD. Suppose, okay, so on RD, so the point, so why don't I postpone this? Let me finish what I was saying and then I will come to this. Okay. This is something we will do. Let us finish that. We will check countable additivity on the algebra by that criterion which I showed just now. And I will come to you this question. Okay. So if I forget, remind me. Let me do this first. Let me just check this condition. It is very easy. On the algebra to check countable additivity, we just have to check these two conditions. So let's do that. Well, how do I check that? So let me erase this thing here. Okay, so let us take. So what do I need to do? Let A be in the algebra. Okay, given epsilon, want okay such that first let us start with the case where lambda of A is finite. So then given epsilon positive, we want a set B in the algebra and K compact such that B contained in K contained in A and such that B contained in and lambda of B is bigger than lambda of A minus epsilon. Okay, so this is what I want. Now, how do I ensure that? It is very easy. To start with, A is in the algebra, so you write it as A is R1 disjoint union Rn. Okay, where each Ri, you take one of the Ris. R1, how does it look? It looks like A1 B1 cross A2 B2 cross A sub D, B sub D. Okay, it looks like this, right? So it's all finite. So all these are finite. Now I want a compact set contained inside and an algebra element in that, which such that the measure is only slightly smaller. How do I do that? So what will I take as the compact set? Let's take the K1. K1 will be what? I want a compact set contained in it, but not too small. What do I do? The problem with this is it's not compact because you have openness on the. So in RD, you know, compact sets are same as closed and bounded. This is bounded. All the AIs and BIs are finite. Because I am doing the case when lambda A is finite, so all these are finite. So what I do is I just go a little bit further, right? So if I just do, I can't take A1 because then it will not be contained in that. So let me take A1 plus some delta to B1 plus A2 plus delta to B2 and so on. So suppose I take this, then what can I say? And then what do I take? B1, let me take B1 to be just, I want an algebra element which is contained in this. So very easy, I just make it open on the left.
Sir, if we don't add delta 1, delta 2, or delta 1, then also like it can be closed like intervals, like we can take closed A1, comma B1 like that.
Right? Closed A1, K will not be contained in R, right? So there was no delta 1, I just miswrote that. It is only delta. Okay, so let me just write it again. So if I make it A1 closed, then that is not in R1. So that will be, I want a set which is contained in R1, right? Do you understand?
Mm.
Oh, okay, that was
Okay.
one, it was comma. I myself could not read what I had written.
Uh, Sir, I mean, not to be pedantic, but we still need to explicitly spell out delta, right?
Oh, yeah, I have not finished. I am not
Right.
done yet. Yeah, you're right, yes. So we have to, suppose I take this delta and then I take the B1, which is just make it open there, that is still contained in it. I am just dropping the left hand points. So then this is compact. This is in the algebra. I mean, it's a rectangle and lambda of B1 is B1 minus A1 minus delta into B2 minus A2 minus delta dot BD minus AD minus delta. Whereas lambda of R1 is, okay, so this is bigger than, is it close to B1 minus A into B2 minus A2 into BD minus AD? If delta small. I don't need to figure out how small I need to make delta. It is clear that as delta goes down to 0, this approaches this. So if delta is small, then this is bigger than this minus an epsilon. Okay, so maybe it's not visible. I have a minus epsilon there. Because if delta is small enough. Okay, so if you want, make it smaller than minus epsilon by n. Just so which is same as lambda of A1, lambda of R1 minus epsilon by n. So now you take the set. What I want K is, I want K to be K1 union So this is for 1. You do similarly for R2. You will have a K2 and a B2. R3 will have a K3 and a B3 and so on. So you take K to be K1 union, K2 union, Kn, and B to be B1 union, B2 union, Bn. So since Ki is contained in Ri, Kn is contained in Rn, and that is my set A. It is clear that K is contained in A and B is contained in K. This is compact. Finite union of compact sets is compact. This is in the algebra. Finite union of algebra elements is in the algebra. And lambda of B is lambda of B1 plus up to lambda of Bn. And these are bigger than lambda of R1 minus epsilon by n plus dot 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 lambda of Rn minus epsilon by n. So overall, I got something what I wanted, lambda of A minus epsilon. Okay, it's very easy. I mean, there is nothing to write. I mean, it's very easy to see that I can just make it slightly smaller and all things compact and so on. That's all. So that's how you verify this condition. There was another condition. What happens when A has infinite measure, but that is even more easy. So the other thing is when A has infinite measure, if A is in the algebra and lambda of A is infinity, then A is R1 union Rn, where one of the Ri's is infinity, right? Because the lambda of this is sum of the volumes of this, so one of them must have infinite volume. So let's say R1 is infinity. Let us say R1 volume is infinity. Okay, so that means R1 has an infinite side. Okay, so one of the sides of that rectangle must be infinity. So it is very simple. You take Bn to be R1 intersected with minus n raised to the power d. So if I were to write a picture in 2 dimensions, I have an infinite rectangle. Maybe it is infinite in only one direction. So this is my R1. What I am doing is I am taking its intersection with minus n raised to the power d, which is a large box like this. Okay, I did not put the dotted side on the bottom. I should have put a dotted side there. This lower end is dotted because it's all algebra elements. So the intersection of that is this, and that clearly what happens to that, the length of that, I mean, one side length will go to infinity. So it is, yeah, I don't want to waste time saying this, but this goes to infinity. And is finite at all times. At all times it is finite because it's contained in minus n into the d. So of course Bn is a subset of A. So what we have is we have algebra elements. Of course this belongs to the algebra and it is a subset of the set we started with. Okay. So it's an algebra element being intersection of rectangles. It's a rectangle itself. It's contained in A. It has finite measure, but it is going to infinity, and that's for the other condition I wanted. So we have checked the conditions for countable additivity. Okay. So any questions about this? So this shows what we have done is check that we didn't directly check countable additivity. We checked this lemma, conditions of this lemma we have checked, and therefore it extends in a countable additive way. That's all. Okay, so any questions about this? No? Okay, so in that case, so let us then continue. So there was this question. So let's me now address that question, okay, which I said I'll do afterwards. So what? Okay, so from here, what do we get? We get the conclusion. So hence, LD star, which is the set of collection of sets satisfying this is the measurable sets, okay? Collection of measurable sets. We call them measurable sets or Lebesgue measurable sets. Always that is what it means. That is those that satisfy the cut condition. So this contains the Boyle sigma contains the sigma algebra generated by the algebra. That is what we have said before. If we have it countably additive, then this extended sigma algebra contains the algebra and hence the sigma algebra contained by this. So now what we want to say is that this is in fact the Boyle sigma algebra. So why is that the case? Okay, so why is that the case? So let's just write out a proof. This I can leave it as exercise, but maybe once in a while it is good to do some things simple but explicit. So one way we want to claim is clear. So how is this contained in this? That is sigma of A is contained in Boyle sigma algebra of RD. Is this clear? Okay, how do I show that? So take any rectangle. Take any rectangle which is so is this in the Boyle sigma algebra?
Yes, because this can be represented as countable intersection of open rectangles.
Of open rectangles. So you will take it as A1 to B1 plus we extend it a little bit. So we extend it. So we have this left open, right close. So what we are doing is we just extend it a little bit on the top and right. So that gives us an open set, but we extend it by 1 by n and then we take intersection over all n. So then we get exactly that. So these are open. Hence in the Boyle sigma algebra. So countable intersection is in the Boyle sigma algebra. Implies R belongs to Boyle sigma algebra. This implies the algebra itself is contained in the Boyle sigma algebra because every element, any algebra element, is a finite union of rectangles. So if all rectangles are in Boyle sigma, are in Boyle sigma algebra, finite unions of them are also in the Boyle sigma algebra. And since that is a sigma algebra, the smallest sigma algebra containing A should be contained inside that. So one way is clear that sigma A is contained in the Boyle sigma algebra. What about the other way? The Boyle sigma algebra is contained in sigma of A. How do we show this? Okay. So you have to say that, for example, every open set is there. How do we show this? So this is where, I mean, so as one of you pointed out, so in one dimension, what I would do is, I would take a open set and write it as a countable union of intervals. So I would only need to check for each interval. So if I can show which open interval is there in sigma of A, then every open set is a countable union of open intervals. Therefore, it is also in this, and so if all open sets are there, the sigma algebra generated by open sets is there. So all we need is to check that countable sets. Sorry, all we need to check is that open sets are there. So let G be any open set. So the claim is, then write G as a countable union of rectangles. They don't need to be disjoint or anything like that. See, in the one dimension, we had this structure theorem, which is actually special to one dimension. It's not true in higher dimensions. But there we could actually write it as a disjoint union of open intervals. Here I don't care actually. I want to write it as a countable union of open rectangles. But then it follows of these are left open, right closed intervals. Then it follows that G belongs to the sigma algebra generated by this, because each Rn is of course in the sigma algebra generated by A. There is no need to say it. In fact, rectangles are the starting point for that, right? So every open set is there, which implies that the entire Borel sigma algebra, which is the smallest sigma algebra containing open sets, is contained in sigma of A. So that's all there is. So the question is to justify this claim. So how do you show this? That every open set is a countable union of rectangles.
Rn is second countable in general, right?
Yeah. So there is a countable dense set. So how does that ensure this? So firstly, you can forget, because often you would not have worked with the left open, right closed. Can you write G as a countable union of open rectangles or closed rectangles, whichever? Then we can always go from that to left open, right closed. So don't worry about left open, right closed. That doesn't come naturally to think. So can you write G as a countable union of open rectangles or closed rectangles? Something like that.
If we are allowed to use topological stuff,
Huh?
that can count means you have a countable base, and that base can be rectangles, and then you're done.
Okay. So what does that mean? I mean, for people who may not have taken topology, what does it mean to say it has a countable base?
It's 4 o'clock.
So essentially, a base or basis of a topology is
Is it
a
Let
bunch.
me turn it off.
Are you saying something?
No, there is a phone ringing. Let me turn it off. Sorry about that. Yeah, please continue. Yeah.
Right. So I could be wrong, but as far as I remember from the previous course, a basis essentially is a set of, a bunch of open sets that you can use to represent all the open sets in your complete topology. Very clearly speaking.
Okay. So it is like
And
you want, yeah. So you want a collection. So the claim is this. So if G is without using the term, so if G is open and X belongs to G, what we know is that this means there exists a open rectangle let's write tilde for open rectangles containing X and contained in G. So open rectangle means something of the form A1 B1 cross. Okay, so this is just the definition of open, right? So this type of set, how do you ensure that this comes from a countable family?
You can maybe use the rationals.
Yeah, so you can such that we can ensure that AI and BI are all in rational numbers. No harm in that, right? So if there is an open set So imagine an open set like this. Okay, the boundary should be drawn in dotted. So if I have a point here, the claim is that there is a rectangle, open rectangle, I can pick around that which is contained here. But I can also ensure that the endpoints of these rectangles, all the endpoints in all the directions, so are rational numbers. There is no harm. I can always decrease a little bit and find a rational number. So I can do this. So therefore, this collection is a countable collection. The collection of all rectangles with rational endpoints is a countable collection. So this is a so what we are writing is, so G is a union of all these R tilde, so R tilde X, let us say. But that is a countable. They are not. This looks uncountable, but it's actually only countable family of things, right? Only a countably many of these are there. This is actually a countable union. So that is the gist of it. So why you can write G as an open union. There are different ways to do it, but this is one way to say it. That you can restrict yourself to only rectangles with rational endpoints. Then any open set can be written as a countable union of those things. Because anyway, there are only countably many of those things. So any union is a countable union. So that's all. Okay. Any questions here?
Got it. Thank you. Thank you.
So, but there are other ways.
Sir, I'm unable to hear you for some reason.
Oh, is it? How
I
about
think someone is unmuted and then you became kind of inaudible. Now you're fine.
is what about others? Is anybody else having trouble hearing?
Right now it's audible.
Right now it's audible. Okay. Okay, let's let me know if I become inaudible. So what I said was this is one way to go about it. If you look at Stein and Shekachi, they prove another theorem which you can take as a substitute for that nice theorem in one dimension, that every open set can be written as a disjoint union of open intervals. That is not true in higher dimension, but they prove that every open set can be written as an almost disjoint union of open rectangles. Almost disjoint means, or they write as almost disjoint union of closed rectangles, let's say. So almost disjoint means the rectangles don't have intersection in the interior. So this rectangle and this rectangle, okay, they intersect in the boundary part, then it is okay. But it should not be like this. This is not okay. Yeah, so they prove a theorem like that. If you want to, you can have a look at that. We don't need it. So I will not go into that. That's a useful one. It's not useful in topological sense, but in measure sense it is okay because these boundaries will have zero volume. So it is actually a good representation for doing measures and so on. Yeah. Okay. So any other questions?
Sir, sorry, sir, I did not get that. For which purpose this is useful? Like rectangles with.
If they are almost disjoint, it is still true that the volume of the union will be the sum of the volumes.
Yes, yes, yes.
Because the volumes of intersections will be empty. That is the point. So that's why in measure theory that can be useful if one wants.
Yeah,
So
okay, thank you.
yeah, I don't use it. I will not use it actually. Or if I need, I will say it again. Any questions? Okay. So now what I want to do is, so we have done all this. So hard work, some amount of hard work has been done. Now we want to actually get down to Lebesgue measure and understand it. What is there to understand? Well, we have constructed Lebesgue measure. So there are many things that we need to understand. Okay, so let's just. So what is Lebesgue measure? Okay, I had written the definition which I guess. So on RD, we have Lebesgue measure which we denote lambda, or if I have to denote the dimension, I will write lambda d on this, which I will just write LD now. LD star is what I used to write. LD which contains BD. Okay, so this is the Boyle sigma algebra. This is the Lebesgue sigma algebra. So what this contains will be called measurable sets. Whenever people say measurable set in RD, they mean Lebesgue measurable. What is here are called Boyle sets. Okay. So we have this such that for rectangles, it is the usual notion. So there is a unique such thing because these rectangles form a pi system which generate the Boyle sigma algebra. Or I mean, okay. Anyway, we have extended it. So this is the measure. So let us say it that way. So many things to understand. What are things to understand? So let's just mention a couple of them. Let me say in words. So what is the relationship between this and that? So some of the things to understand is then power set of RD. So is it equal? Is it equal here? And if not, if strict inequality, examples to show that. So for all we know at the moment, all sets could be measurable sets. Maybe all sets satisfy Carathéodory cut condition. I have told you that they don't, but we have not actually shown anything that is not in the Lebesgue sigma algebra. Similarly, you can ask, is the Lebesgue sigma algebra same as Boyle sigma algebra? Or if not, is there some set I can show here which is not here? Okay. So this is more for curiosity's sake, actually, in the sense that if you don't see it, you are not at a loss, strictly speaking, because you can just work with this, just, I mean, logically speaking. Of course, it is a bit unsatisfactory if you are, if you, your entire business of, for example, if after 3 years of studying, somebody tells you actually Lebesgue sigma algebra is the whole power set, then you will feel foolish. Why did we undergo all this struggle with sigma algebras and so on? So it is better you know that it is not. Okay, so that is one thing. And what is the relationship between them? More generally, what is the relationship how significant is the difference between, I am phrasing this question in a certain way because I know the answer. So it looks like the same question. Is there anything here that is not here? But in some sense, it's not the same question. Here, what I'm saying is it really different? How different? Okay, when we answer, you will see that in some sense of measure, they are actually not that different. Although this is huge compared to this, there is a sense in which it's not that big a deal. Okay, you can work with Boyle sigma algebra just as good. But these are just for curiosity's sake. But our life depends on some other questions. What are those questions? So either either sigma algebra is inexplicit. We kind of know it only, we don't know which sets are there. So how do we work with them? Okay, in the sense, this is actually becomes key to how you can do anything in measure theory, right? See, the thing is, neither Lebesgue sigma algebra nor Boyle sigma algebra is something that we understand very well. We know some sets which are there, namely, we know rectangles are there, we know unions of them are there, closed sets, open sets, they are all there. But we don't know all the sets there. So how do we work with them? Ultimately, all we know are rectangles. That is, we cannot get away from that fact that what we really understand are rectangles, and anything else we have to understand in terms of rectangles. But how do we understand? I already made the point many times that we cannot write sets in the sigma algebra, say Boyle sigma algebra, in simple terms, in terms of countable unions, intersections, complements, etc. of rectangles. This cannot be done. But still, from the point of view of measure, it is possible to approximate sets by rectangles. That is the point that we will see. So the point here will be that yes, you cannot write the set exactly like that, but you can write it approximately like that from the point of view of measure, and that will be how it will work. So here the question comes. Here comes approximation or other relations between measurable or Boyle sets and rectangles. Okay, so how do we actually work with them? This is very, very important. The first one will be a matter of giving counter examples. It is curious and you will learn techniques there, but this is something that you will really need to work any further in the subject. Okay, so this is what I go on to do next. We will study this. Actually, many of the things I say will also work in a greater generality, where we had an outer measure and then there were two things, right? There was a L mu star, the set of collection of sets satisfying the cut condition, and then it sometimes contained the sigma algebra generated by the algebra. So various questions, many of the things I say will generalize to that situation, but let's not worry too much. It's not so important. It's if you understand Lebesgue measure very well, then that is a good start. Okay, so this is what I will spend this class and the next one maybe on. Any questions? Is it clear? Okay, in that case, let us proceed. So let us, so we'll come to many things. It will not be answered in this order. We will go about it in some order, whatever be the thing. So first, let me talk about something about Lebesgue measure. So let me say first, yeah, what should I start with? I have the measure lambda. Okay, so let me start with what is called a very important. Okay, there are other properties. Okay, so there are yet other properties. Other properties of Lebesgue measure. Maybe I start there. Okay, so let me start there. What are properties of Lebesgue? Why is Lebesgue measure special? What does it have to do with RD? Okay, so let's start with symmetries. Okay, first of all, lambda d of A plus X is equal to lambda d of A for all A in the Lebesgue sigma algebra and for all X in RD. Okay, so this is called translation invariance. Meaning, if you take a set and move it, just slide it along a direction x to some distance, then it will not change its volume. Okay, so this is translation invariance. So A plus X, what is A plus X? A plus X is just you add X to all the elements. Yeah, that's all. It is the set of sorry, A in not RD but A, capital A. So the translated set has the same. It is also true if I, more interesting is if I, what happens if I scale a set? R times A. What is R times A? R times A is the set of all Rx where X is in A. Okay, so this is for all A in LD, and what is R? R is a positive number, or you can take real number if you want. R is just a real number. What happens if I multiply all the things? Will it change the set or not? For example, you take in one dimension, take the interval 0 to 1. If I scale it by 7, what happens? It becomes the interval 0 to 7. So what happens to its length? It increases by 7, right? What happens in 2 dimensions? So a square, both sides will blow up by that factor. So it will go by the square of that and so on. So in general, it will be absolute value of R to the power D times lambda D of A. So this is the scaling relation. We shouldn't say invariance because it's not saying that after scaling it will stay the same. It is telling us how it will. You can formulate it like an invariance, but scaling relation, let's just call it. So here I have allowed real numbers. So firstly, scaling means by positive numbers. But just one more thing, you can also negate a set. If you multiply by minus, it will flip over. That won't change the volume. That's also included inside this. That's all. You can always think of multiplying by real numbers, multiplying by a positive number, and then either flipping the sign or not flipping the sign. So it is two things actually. Okay, so these are some properties. I will prove this. Third one. This is actually less trivial. So maybe I prove these first and then come to the third one. Yeah, so for how do I prove the first one? Why is that true?
You can kind of take the same cover, but also translate it.
Basic point is that, so basic point for 1 and 2, if we start with rectangles, right? If R is a rectangle, then what is R plus X? R plus X will be, everything is translated by, X is actually X1, X2, XD. Okay, X is in RD, X1, X2. So it becomes A1 plus X1, B1 plus X1 times AD plus XD, BD plus XD. You are adding X1 to the first coordinate, X2 to the second coordinate, and so on. So it just shifts like this. And what will be, let's call it T times R. If I take T times R will be, so if T is positive, just let's stick to that case, will be TA1 to TB1 and what is clear is that the volume of this, the standard, the thing that we started with is same as R, because what is this? By definition, it's the length of this times length of this and so on, a product. But X1, when you subtract, you just get B1 minus A1, B2 minus A2, BD minus AD. There is no problem. Here, what happens is, when you do the subtraction, this becomes TB1 minus TA1 times so on up to TBD minus TAD, which is T to the power D times the volume of it. Because of that, so the point is this property is there for rectangles, and therefore, if you go through the outer measure and so on, outer measure itself has this property. for any subset, as long as I am applying only outer measure. So now I leave you to check this. So this is what you need to check, and it is simple. The point is, as you already said, one of you said, if you cover A by some rectangles, you just use the translations of them to cover A plus X. Or if you cover A by rectangles, use the scalings of them to cover T times A. That's all. Okay, so that's how you get this. So, and what is lambda? And lambda is just the restriction of lambda star to Lebesgue measurable sets. So this sigma algebra. Hence, it also has the property. So outer measure itself has this property. So it's no surprise that when you restrict it to the sigma algebra, it has that property. Okay. Any questions? Or is it clear? So this is very important, and this is the key reason why this is the we wanted it that way. We wanted some volume, and implicit in our. I never said it before, but implicitly we had in mind that volume should not change if you translate it. But there is a third property which is actually less obvious. Suppose A is a subset, A belongs to LD, and let us say Q is a D cross D matrix. What I do is I apply Q to A. I do a linear transformation now. What is this QA? It is just apply Q to all the elements QX, X in A. So we have an RD, right? You have a D by D matrix. You can multiply. So you can transform the entire set via this linear transformation, which is left multiplication by Q. What happens to your volume? Any guess? What will it be? What should it be?
Determinant times the volume.
Determinant of Q. We should put an absolute value because it has to be non-negative times the measure of this. Okay, if it is a singular matrix, it becomes 0. But otherwise, so particular case, so maybe I should write. Okay, I'll write here. In particular, lambda d of QA is equal to lambda d of A if Q is an orthogonal matrix. So orthogonal matrix means, for example, rotations. That is not all, but rotations. So if you just rotate something, it doesn't change. Another special case is lambda d of QA is 0 if Q is not singular, because then determinant Q will be 0. Yeah, but first one is important. Orthogonal invariance. Volumes are not only unchanged under translation, but that is also unchanged under rotations. If I just rotate an object, it should not change its volume. So that's what is being said here. Okay. So how do we prove this? So this also is a very important symmetry property of volume. How do we prove such a thing? Pretty much, I would say it's the same, except there is one point which has been missing from the beginning, which I will probably skip because I don't want to spend too much time on it, and you should definitely fill it up by looking at the book. But here is the point. So for 3, could be done exactly the same way. By same way, I mean as 1 and 2. If only we could check that lambda d of Q times R is equal to determinant Q times lambda d of r for all r rectangles and Q is a d cross d matrix. If I could do it for rectangles, then again exactly the same thing. So if I can cover A with rectangles, I will cover QA with Q dot R. But the problem is this, actually this is a little bit tricky because it's actually one thing that we have actually been, I never mentioned it, but it is, we said that our new notion of volume, which is extended a lot, agrees with our old notion of volumes because lambda agrees on rectangles with whatever we thought. But actually, we know that for rectangles which are axis parallel. So let's say in 2 dimensions, if we have a rectangle like this, then we know that the area of that is length times breadth. But what if our rectangle is like this? Do we know that if this is L and B, is the area equal to, is lambda of R, if this is R, equal to A times B? Is this true or false? Sorry, not A times B. This is L times B. This needs proof. It is not easy because you cannot say, okay, it is, but how do we know? Even for this rectangle, because we are not using these rectangles in the covering. You remember our definition of outer measure is via always. Whenever I was saying rectangle, I meant axis parallel rectangles. Everywhere we only use them. We have not used these rectangles in defining the outer measure and so on. So now if you want to calculate the volume of this, you have to go to the definition of outer measure. Cover this with axis parallel rectangles. You have to cover this with axis parallel rectangles. How do I do that? Maybe I make a very fine grid of, it's kind of easy to imagine that I will cover it like this with rectangles so that I don't exceed too much. It seems plausible, but you have to write a proof for this. When you do that, will you get L times B? It's not so obvious because what are you going to do? You are going to take the sum of the areas of these rectangles, which are the length times breadth of those things because they are axis parallel. But when you add them, will you get this B times this L? Well, you should, but it's not entirely obvious and it needs proof. We will skip. I don't think there is anybody who really doubts that this will be true. You should read a proof or produce one yourself, but let's assume that is the case. So then you can do it for any region. So once you do that, after that, so let me just skip it. That's all. Okay. So all I want to say is that it is true. You have to do it, and you can do it by like this kind of thing. You need an argument, but it is a bit. I think it's not so clean to write it down in higher dimensions. But there is no real thing lost. So maybe we will just skip that. So this relates to another thing. Another thing very closely related to another thing. We used as basic building blocks axis parallel rectangles. Was that important? So in other words, could I have used, would my life have been simpler if I had allowed rectangles oriented in any direction in my defining outer measure? Well, not entirely. It is not obvious because somewhere else the problem will show up. You see, it might seem to you that it would have made things simpler. Why not assume that all all rectangles, whatever be the orientation, will have the usual notion of area and volume, and why not use that in defining outer measure? Well, now your infimum becomes over a much larger class of things. And it becomes, some things become less obvious. For example, becomes less obvious to prove that even an axis parallel rectangle, its volume is not reduced because you are taking infimum over all sorts of coverings. Can you show that it is not reduced? So the same problem will show up in a different place. You cannot avoid it. So you can also ask, instead of rectangles in various directions, could we have used discs to cover? You can, but again, it's not entirely obvious. So these things need a proof. So now that we have done so far, the best is to just fix this and prove that for rotated rectangles you get the same, and then you are fine. Okay, I will probably skip this. But any questions? So this is the volume of parallelogram, by the way. I mean, you probably know this, right? I mean, if it is a cube, this becomes a parallelogram. Pipe. Okay.
So does every matrix on a applied on a rectangle lead to another rectangle or a parallelogram? Is that given?
So yeah. So linear transformations transform parallelograms to parallelograms, right?
Right.
Yeah. That's always true.
Sir,
Huh.
it can happen that Q is not orthogonal as well as not singular matrix.
Yeah. So that's why it becomes parallelogram. If it was orthogonal, rectangles would become rectangles.
Yes.
In general, it becomes a parallelepiped. So if you take a linear transformation, so for example, so what happens under a linear transformation? A square like this may become, let's say, this point. So if the column, so if I multiply by q, which is so this is they need not be in first quadrants. Let's say this 1, 0 gets mapped to the first column, which is this one. 0, 1 gets mapped to the second column, which is this one. So what happens to this region? It will get mapped to these lines. So this line will go to this line, and this line will go to this line, and the whole square will go to this parallelogram. And the area of a parallelogram is given by the determinant of the sides.
Sir.
Huh.
So about the whole disk idea, because that's something I was thinking of when we started off with this. And if we look at open disks and stuff, then we are essentially so we used LORC rectangles for a very specific reason, that their complements are also very cleanly a bunch of LORC rectangles. But would the same be true for disks?
No. That becomes going through this algebra condition with the open disks, I think, is probably very bad. So it is better, one way is better, do this with rectangles. Now show that even if you take infimum over disks, you get the same outer measure.
I see.
So then you don't do all the algebra business there. So you say that you get the same outer measure, after which everything has to be the same. Because the way you restrict the cut condition, everything depends on the outer measure. So as long as you have not changed the outer measure, you are fine.
All right.
But disks are very tempting to start with because they automatically have rotation invariance. Yeah, but to my knowledge, it will just get complicated. So it's better to use rectangles.
Got it.
Any other questions? So these are the main symmetry properties of Lebesgue measure, and this is the unique measure with these properties. Well, up to multiplication. So I did not say this. Okay, maybe now I say it. If mu is any measure on L or B such that mu of A plus X equal to mu of A for all A in L. So now let's just say it on the Borel sigma algebra itself. That's the smallest one. Even there, if this is the strongest statement, if I have a measure on the Borel sigma algebra such that it is translation invariant, then mu is actually a constant times lambda. That is, mu of any set is this constant times lambda of it. Okay, and for all A in the Borel sigma algebra. So you could also allow zero measure and infinite measure. So I allowed C equals 0 infinity. Those are not the interesting case. The only translation invariant measure is that. Why? This is a multiple of this. Well, the point is, okay, so maybe I just leave it as exercise. So I'll move on to something else. This is a fact. So basically, you just see what happens to rectangles. You multiply by constant so that mu and lambda agree on rectangles. Once they agree on rectangles, that's a pi system which generates the sigma algebra. Therefore, they will agree on the sigma algebra. That is one way of doing it.
Sir.
Ah.
So what is a pi system?
Okay, forget pi system. Let's say suppose mu and lambda agree on the algebra generated by these rectangles. Then they have to agree on the sigma algebra generated by them, namely in the Borel sigma algebra. Right? That is what we showed. If two measures agree on an algebra that generates the sigma algebra, then they are.
No, but what is a pi system? You've been using this term.
Yeah, no, that is another thing. So here in the class, I only introduced algebra and monotone class. But one could equally well use some other classes of sets. So pi system and lambda system is another class of things. Pi system is a collection of sets which is closed under intersections, finite intersections. So for example, the collection of left open, right closed intervals form a pi system because you intersect two of them, you get another one of the same kind. So there is pi systems and there is something called lambda system. One can use them in place of monotone class and algebra, but it's equivalent actually. You don't need to. It's enough for you to know monotone class and algebra. Okay. Any other questions? Okay. So then let me go on and go on to other properties of Lebesgue measure. So these were the symmetry properties. Now we go on to this other type of properties. What is this Lebesgue algebra, Borel sigma algebra? How do we understand measures of sets in terms of measures of nicer sets like rectangles or open sets and so on? So that is our question. Oh, okay. So so here there was so this part maybe I just change it. So here it is symmetry. So I now go to a new page. What is this level? Okay, so now let's come to other properties of Lebesgue measure. So I will go on putting down a few properties and then you will have to, I'll try to be organized, but nevertheless you have to spend some time thinking about these things to organize it in your own mind. So we have the Lebesgue measure. So we have RD with LD containing Borel sigma algebra and lambda D on LD. So lambda D of R is the usual. So first I will say something called outer regularity. of Lebesgue measure. What it says is that for all measurable sets, the measure is the infimum of measures of open sets. That contain the set. So you can approximate in terms of measure. So another way to say it is, if you give me an epsilon, I can find an open set containing A which has only an epsilon more measure. Okay, lambda G. This infimum means that if I give you epsilon, you can find a G such that lambda D of G is less than lambda DA plus epsilon. So in other words, you can approximate A by an open set which only has a little more measure. That's all. Okay, that's what it means. So there is also, since I got outer regularity, there is also something called inner regularity. So let us maybe state even that also. And then I can prove that inner regularity is coming from the inside. It says that for any Lebesgue measurable set, there exists, to write it similarly as before, lambda D of A. You can approximate it from inside by compact sets. So it is the supremum of measures of compact sets K, sorry, not containing, but contained in. Okay, so you might think that the natural counterpart to that would be to take K closed. Indeed, you can take K closed. This is a stronger statement. Why is it stronger? Because it is telling that we are even approximating by a smaller class of sets. All compact sets are closed. If you were to say K closed here, that would be allowing yourself more sets. But we are even saying that even with compact sets, you can approximate A from inside by a compact set so that the measure is not too small. In other words, give me an epsilon, I can find a compact set inside A such that its measure is at least lambda D of A minus epsilon. That's what it says. Okay. So maybe we prove this first. These are very important properties of Lebesgue measure. How do we prove this? Well, first one is quite easy. So lambda of A. So find Rn left open, right closed intervals, rectangles, such that their union covers A and their sum of their volumes is less than lambda D of A plus epsilon. So this we can do by definition, because lambda D of A is lambda D star of A, by the way. See, for measurable sets, the measure is same as outer measure. It's just the measure is just the outer measure restricted to this nice class of sets. That's all. So we can find Rn such that their union contains A and the sum of volumes is at most this plus epsilon. You can do that. Now you enlarge Rn a little bit. So let's make it Rn tilde, which is open, and such that Rn tilde volume is not too big. Let's say it is bigger than volume of Rn, but by at most epsilon over 2 to the n. Okay, so do it for all n. So for each n, we have a left open, right closed rectangle. Now you make it open by enlarging it a little bit, and you can make arbitrarily small enlargement. So you make it so that this enlargement is like this. So then what happens? Then G equal to union Rn tilde is open. It's a union of open sets, hence open. Each Rn tilde is open. Therefore, union Rn tilde is open, and if you look at the lambda of G, that is less than equal to sum of lambda of Rn tilde, which is same as the sum of volumes of Rn tilde, but that we know is at most volume of Rn plus epsilon over 2 to the n. Okay, and what is the sum of volumes of Rn? We know that that is at most lambda d of A plus epsilon. And what do this epsilon by 2 to the n add up to? Another epsilon. So we get that this is this. So this proves outer regularity. Right? Given any epsilon, I found a G open which contains, G is open and also G contains A because Rn tilde is even larger than Rn. So nothing is lost. Okay, that's the outer regularity proof. Any questions? It's just going back to the definition. Okay. So how do you show inner regularity? So to show inner regularity, what we do is the best is to just say complement or something like that. But it may be, so suppose, let me put it this way, suppose A contained in RD, sorry, a measurable set, not any subset. A is a measurable set. And A is bounded. First, let me assume that A is bounded. Then taking complements is easy. So find them such that A is contained in minus m to the power d. Let's give it a name just to write it as qm. Qm is this cube, closed cube. Okay, suppose A is bounded and then you find this bounded, so it will be contained inside this rectangle for some m. Then you look at qm minus A. It's like a complement of A. The thing is, we want to say complement. See, I want A to contain a compact set, right? So what I will want to do is I just take a complement which is contained in an open set. Then I take complements. That is one way I get a closed set inside A. But here is just, let me write it out. Qm minus A is, so then there exists G open such that this Qm minus A is contained in G and lambda of G is less than equal to lambda of Qm minus A plus epsilon, right? By outer regularity. By outer regularity, I can take Qm minus A, which is will be contained in an open set whose volume is not too big. Therefore, what does that mean? If I take Qm minus G, I'll take that to be K. Okay, so this is firstly compact because Qm is compact and G complement is closed, so closed intersection compact is compact. So this is compact. K is contained inside of. So G contains Qm minus A. So where is Qm minus G? I say it is contained inside A. Let me check the time. Okay, 4:52. So this is your compact set, and then blah blah blah. Okay, maybe I will skip. It's getting a bit boring. So it's written in the notes, or maybe okay. Let me do it anyway. So what happens? This is true, and lambda of k will be. So k is compact, is clear. Lambda of k will be lambda of qm minus lambda of g, and we know that lambda of g is less than equal to this. So this is less than equal to, is greater than equal to lambda of qm minus lambda of qm intersection, sorry, lambda of qm minus a minus epsilon. But that is, this is lambda qm minus lambda a, so this is lambda a minus epsilon. So that is the proof of inner regularity. Okay, so this is a very important properties, outer and inner regularity of Lebesgue measure. Any questions? Actually, lots of measures will have this property, and well, anyway, that's it. So, any questions so far? Okay. So if not, then let's continue. So what other properties do we have? So let me have a few minutes. So let me just say something interesting about the Lebesgue and Borel sigma algebra. Okay. So this is not the key point. As I said, I'm not going to do it in a particular order. So here is another point. So given in fact, I'll say this. Let A be a subset of the RD. Okay. Then, one hand, A is in the Lebesgue measure, Lebesgue sigma algebra, if and only if something, I will say in terms of Borel sigma algebra. There exists B and C which are in the Borel sigma algebra such that B is contained in A and A is contained in C, but they have the same measure. Okay. So Lebesgue measurable sets are exactly those that can be sandwiched between two sets, Borel sets of equal measure. So this tells you in some sense that Lebesgue measurable sets are not that much. I mean, so they are just sandwiched between two Borel sets of equal measure. So actually pretty much these are the same. I mean, they are very closely related. Is the statement clear? Okay, so let's see why this is true. Let's give a proof. So let's go, which way shall I go? Yeah, okay. First of all, before proving anything, so basic observation. If let's give it different name, if S is a subset of RD and it has zero Lebesgue measure, outer measure, then S belongs to the Lebesgue sigma algebra. Okay, so this is a basic simple observation. So why is this true? Why does any set with outer measure 0 belong to the Lebesgue sigma algebra?
It will trivially satisfy the Cartesian cut condition.
Exactly. So for any E, so we have to look at what lambda star of E is greater than equal to lambda star of E intersection S by monotonicity. By monotonicity, which is this is okay, right? So this is okay. But lambda star of, oh sorry, no. What did I say? Is greater than E intersection at complement. Let's say. Is okay. you take for any E in RD, E intersection S complement is a subset of E. By monotonicity, this is true. On the other hand, E intersection S is again by monotonicity is less than equal to lambda star of S, which is actually 0. Right? So you add, what do you get? You get, if you add, you get lambda star E plus 0. If you add the two, you get lambda star of E on the left side greater than equal to lambda star of E intersection S complement plus lambda star of E intersection S. Hence, cut condition satisfied. So that is the source of this observation. Okay. So what is the relevance of that? Is that clear? Every set with zero outer measure will be in the Lebesgue sigma algebra, not so in the Boyle sigma algebra. So based on this, let us prove the this way implication. Okay. Suppose B and C are in the Boyle sigma algebra. B contained in A contained in C, and lambda of B equal to lambda of C. Okay. So then A can be written as B disjoint union A minus B, right? See, B is here, A is a little bit larger, and C is a bit larger. So this is C, this is B, this is A. So what I am writing is A is B union with the parts of A that are outside of B, A minus B, okay? So now the thing is, this is in B, which is anyway subset of L. So B is Lebesgue measurable. Now my point is A slash B is less than equal to lambda star of C slash B, because A minus B is
It's 5 o'clock.
contained in C minus B, right? But what is lambda star of C minus B? It is lambda C minus lambda B. Because C and B are both Boyle sets and hence measurable, Lebesgue measurable, this is lambda of C slash B, which is lambda C minus lambda B, which is 0. Therefore, this is something, so this implies that A minus B also belongs to the Lebesgue sigma algebra. So B is in the Lebesgue sigma algebra, A minus B is in the Lebesgue sigma algebra, hence A, which is the union of those things, also belongs to the Lebesgue sigma algebra. Okay. So I showed the this way implication. I will show the other way and go on to further properties next time.
Sir.
Okay.
So
We just say that the lecture stops here. We can take questions. Yeah.
right. Sir, so this the way this relationship has been written. Oh, right. My bad. So lambda A is not involved, right? I miswrote that.
No, there is no lambda A. We can't write lambda of A.
Precisely what I had in mind. So yeah, my bad. Okay.
So exactly. So though here A in LD by definition is in terms of lambda star of A and its intersections with terms of outer measure. Any questions? Okay, so okay, so attendance is going further down every week, I see. Well, anyway, I have already made the point. So, by the way, another homework is up on the web. So, I made the deadline a bit late since many of you are coming back and all that. That's what I heard. So, okay. So, if there are any other questions, I can take it. Otherwise, we can close.
Sir?
Yes.
In the Homework 2, question number 3. I think one notation mistake is there. F equals to sigma A. I think that would be sigma S.
1 second, 1 second. Let me go to the Teams and see the. All right, I have it on my computer. Homework 2. Okay, so which problem?
Problem 3.
Okay. Say what is the problem? Oh, sigma of S.
Yeah, I think
Okay,
this
you
should
are
be
right.
small correction.
That is correct. So in third problem, it says S is a collection of subsets and if it is sigma of A, it should be sigma of S. Okay, let me correct that. Let me correct that. Okay. Any other questions? Comments?
Sir, I have another query. Like when I want to say to recover something from recover means can we derive like that?
Derive what? Sorry.
Like here one point is there, can we recover A from mu? So is this meaning like can we derive A from, or can we get the properties of A from mu? Like
No. If I tell you mu, can you find out what is F?
okay, yeah, okay, got it. Yeah.
You have to get the function itself.
Okay, yeah, okay, thank you.
So whether F can be expressed in terms of mu, that's the question.
Yeah, okay.
All right, thank you, sir.
Okay. Okay, so then we'll close the meeting now. So by the way, if people have questions which they want to ask separately and so on, I am open to it. You just have to write me an email and let me know if you have any questions and so on. Okay. All right, we will stop here.